Hello, everybody. My name is Blake Veneer, and I'm going to be doing a series about what I'm calling spacetime particles. And we're going to be looking at how an Aether model can be used to resolve some of the unanswered questions in physics, especially that of dark matter. So, in this first one, we're just going to be going over the problem in current physics. But the series plan is I want to just talk about, in my opinion, why we are failing to make progress, then what we would need to actually continue forward with our understanding of physics, and then we will talk about what is wrong with current Aether models, and then together we're going to start to develop an Aether model that will actually work and not violate, some of the experiments that have already shot down other Aether models. Um, so what we really need to make progress is some new theories, in my opinion. If you look at in the 1900s with Einstein, there was kind of they were making progress, but it wasn't until he developed this new idea that we really were able to make a big step forward. And if you look at our progress in physics, right now the standard model is the most accepted theory out there. And, it had contributions from Maxwell's equations in the 1860s. Special relativity was 1905. Quantum field theory, 1920 to kind of 1940. Then they added the electroweak theory. We discovered quarks in 1968. We kind of finalized in quantum chromodynamics in 1973, and then later discovered the gluon in 1978. We then got the W and Z bosons in 1983, and then the top quark 1994, and finally the Higgs boson in 2012. After 1973, with the addition of quantum chromodynamics, there really hasn't been a whole lot of theoretical additions to the standard model. And that is kind of one of my big concerns. And then you can see general relativity was 1915, and they're not even part of the standard model. Now, there's other theories out there that is really trying to unify the two, such as string theory. And for a while, that had a lot of momentum, and they were pretty certain that that was the answer to everything. But since then, I feel like it's kind of petered out. And I think one of our biggest issues is reliant on current interpretations of equations. Now, I think, and so we really need to question everything. And I'm not saying we need to question, experimental evidence and what we've seen in the lab, but I'm saying that if we have poor interpretations of equations, or if we're relying on too much of an equation to dictate how physics is actually happening, I think we're going to run into a lot of problem, like the collapse of the wave function. I remember in college, I asked my quantum professor what was actually happening, how this was possible, and kind of the answer I got was, this is just something that we accept. And that is a horrible answer. And I don't know how many other students had asked about the collapse of the wave function. It's just like hand wavy answers, or, there's interpretations, but relying on this as a cornerstone of our understanding should be a huge red flag. Now, as far as the anomalous magnetic moment goes, there's been a lot of recent developments there as far as the G2 experiment wrapping up and the standard model having some updates to the theoretical predictions. My concern here is that the experiments are doing a wonderful job taking lots of data. They're doing blind analysis, and they're getting results that are pretty much bias free. However, with the experimental or the theoretical calculations, we have these equations that are very complicated. I think there's like 12,000 plus Feynman diagrams in order to look at all of the different interactions or account for all the different interactions to calculate the muon magnetic moment. And there's actually a video on this, but that I can't remember, I saw briefly. But the concern would be is that if our target, experiment is here, and, we first start with a value of our theory here. And then if we have all these different interactions or different calculations we can add, we can start to choose which paths lead us closer and closer to the experiment value, right? So like, I'm concerned that ultimately that we're getting this really close agreement, but it's because we've been, it's not like maliciously doing this, but we're just like using the experimental results to bias the decisions that we're making in the theoretical model. And we're eventually getting these very close results, not because the theory side has been in the dark and calculated perfectly, but because they're kind of inching closer and closer towards a value that the experiment has results. But yeah, there's another video out there that explains a lot better, but that's just something I'm concerned about. The other thing that would like to kind of touch on is that what theories can we actually extrapolate? Now, special relativity is assumed to be perfect, right? But in reality, and so we have lots of experimental validation of special relativity, and I don't think anybody would question that. However, just as an example, we have looked at special relativity in like the LHC. We have these particles going to very high energies, and we're smashing them together, and there's no problems there. The thing that I want to point out, though, is that special relativity, the important aspect there is momentum, not just velocity, because LHC's like slamming these particles at close to the speed of light. But the momentum that they're actually generating in the LHC is incredibly small. I think I did a calculation. I don't even want to report it here because seems so small and ridiculous. But like if you were to have a perfect baseball that could absorb all of the momentum from the beam on the LHC, I don't even think the baseball even really moves when it takes a full collision from the LHC. We have terawatts, it's a tera electron volt beam energy, but when you transfer that to the real world, it's, what we live in, it's very, very small in terms of momentum. And so what I'm just proposing is that we have validated the special relativity for low momentum, maybe high velocities, but low momentum conditions. And where can we actually take that on higher momentum systems? And also same thing for general relativity. We have very good agreement in theory and experiment for looking at light deflection or light bending around the sun. We have gravitational lensing, gravity waves. So we would like to think that general relativity is perfect. However, and so the problem though then comes in that we extrapolate that to like say black holes or something. And then we even go to singularities and everybody starts freaking out. But where are we actually allowed to extrapolate general relativity to? We've had measurements of black holes, like we have images of them, but we're not even close to seeing the photosphere. So maybe general relativity breaks down much further from the event horizon than than we currently think, because we really don't have data at that point. So anyway, we might talk about that more, but just some things to kind of think about right now. And another point is a lot of theories in human history has been like, oh, that's interesting. What does that mean? And then they develop like, understanding. They measure it a bunch. They have, very precise, detailed work, and they come up with these physical phenomenon that they get named after. But we're kind of running out of that because in order to understand these more complicated things, we need more energy. And that worked really well in the 70s when we were finding particles left and right. But we need to be more focused on our effort because it is much, much harder to discover these things. And even if we do have the right energy, if we don't really exactly know what we're looking for, then we might miss it in the loads of data that we're collecting. And so we really need to have, a good solid observation to help us push forward into the next layer of our understanding of physics. Now, just like quickly to look at the LHC, LHC was $5 billion just for the particle accelerator part or something. I don't know how accurate these numbers are, but I think it was like 4.3 billion, whatever that included. And then another 13 billion for the detectors. And what did they expect to get from the LHC? They expected to get to confirm supersymmetry. They expected to discover new particles, or at least they hope for. They would like to confirm the Higgs particle, maybe find other dimensions, discover new interactions, something about dark matter or dark energy. Well, it turns out that they didn't get supersymmetry. No other particles were discovered. They did get the Higgs, which is nice. There's no other dimensions or new interactions, and then nothing about dark matter or dark energy. So this huge investment, and really they only found the one thing, the Higgs particle. And like I was saying before, it's too expensive, too challenging to just hope to crank up, some power knob to find new discoveries. Like I think, especially when you are accounting for how much data the LHC is producing, like you could lose exactly what you're trying to find if you're not careful there. So we want to move forward. We need to have a new experiment. And what would my perfect experiment look like? Well, I would like to have clear evidence of a discrepancy. I would like to have multiple ways to measure this, or at least verify this, like different, measuring the same phenomenon in different cases would be nice. So it's not just like one unique thing where something behaves interesting. And then we would like to make sure that this experiment or this result is verified by many, and it's measurable and verified by many. And so there's a lot of times where scientists or group of people will measure something unique, and then they will be unable to reproduce the results, or no other lab can reproduce the result. And so it's the validity of that measurement goes down substantially. So now, what would be a clear discrepancy? I'm just saying, like, imagine if we could say 20% difference in theory and experiment. That would be amazing. If the LHC produced something like that, we would be very excited. Now, what's the budget? Well, we really need to make progress. So I'm going to say for this experiment to solve our current problems, let's just say we have a galactic budget. Basically unlimited. And so with unlimited budget, what could we do? Well, we could make solar system size colliders. I think string theorists want to do this to, look at the Planck's length size stuff. I don't know how big the collider was. Was it the size of the Earth? Was it the size of the solar system? I don't know. It's huge. Now we could do solar system size gravity wave detectors. Well, they're actually launching a new detector here, and that will be a solar-based gravity wave detector. Not quite solar system, but that's coming. And then others, like, I'm sure if you gave scientists unlimited budget, they could come up with all sorts of ideas and stuff there. But really, we do need something. And actually, I think we already have one. And so what? Do we already have this that satisfies all of these requirements? Well, it turns out that we have an experiment that is the rotational curves of the galaxy, and the discrepancy there. We basically can look at the rotational curves of the galaxy, and they are way different than what we would theoretically predict. So how does this work? So in a solar system, we have the sun, and we model that as the point source. And so we can look at this here. Let's say the sun's at the center, and what we expect is that the velocity falls off, Earth. This is now this is curving up, but that should not be curved up. Anyway, so this is what you'd expect. When the sun is modeled as a point source, we would expect the velocities of the planets and any other bodies around the sun to fall off with distance from the sun. Okay, and so now what do we see? How would we expect galaxies to behave? Well, galaxies aren't quite as simple as a solar system because there's a lot of more stuff in there. So if we look at the same thing here, as you are moving away from the center of the galaxy, we are actually seeing more mass, or we're being influenced by more mass. Whereas as you're moving away from the sun is kind of a constant. You get more, like you get Mercury and Venus, but their mass is negligible compared to the sun. So its point mass is pretty close. But because as you move away from the center of the galaxy, we get more and more mass, so the velocity actually starts to increase. Now you're eventually going to get to a point where the addition of new mass is going to start to decrease, and you're going to, a point source like center is going to be start to become a closer approximation. And so we get further away, less mass starts adding, and we start to get a decrease in velocity speed, and that's going to fall off, something like that. So this is what we'd expect. And what do we measure, though? We measure kind of what we expect. Velocity starts to increase, and then it starts to fall off, and then it does something like this. Now, there are multiple measurements, multiple galaxies, and they've looked at this all over. Sometimes they go like this, sometimes they go like this, but basically you have this huge discrepancy between experimental measurements and theoretical predictions. And this really should be enough for us to focus on making progress towards the future. So how do we actually resolve this issue? Well, general relativity has two parts. It has the first part is how space-time bends and what is inside of space-time. And so we can control these two parameters in order to solve the problem with the rotational curves. Now, Neil deGrasse Tyson made a point here that what this delta over here is a misunderstanding or a lack of knowledge about the gravitational effects, or what is influencing the velocities of these planets and solar systems. And so what we are looking at is a lack of understanding of gravity. And so we should call this problem more dark gravity instead of focusing on, like, people would immediately associate this with dark matter. The problem with dark matter is that there's clearly a problem, but dark matter implies that there's association with mass or something like this, whereas dark gravity is more of a open-ended interpretation or open-ended problem statement, and I think it leads to less biases in the future. So really, yeah, I really much agree with Neil on this one, is that dark gravity should be how we're referring to this problem. So now we have a couple current theories out there, and it is dark matter is the first one. Dark matter is working towards adding more stuff into space-time to change how it bends. And so this is relatively easy for us to do because we can just add more mass in any way. We could do Newtonian approximations for the galaxies, which simplify the equations quite a lot. But in order for dark matter to work, we have to add a lot of mass. So let's just say what we see is 15%. And then dark matter. So if you look at solar systems, you can estimate the amount of mass from the suns and the light and everything like that. We would assume that that is 15% of the universe, and then dark matter makes up 85%. This is a huge, huge number. And to me, it is crazy that that even makes, like, that's not throwing red flags. We've never successfully predicted anything by just throwing a bunch of mass at it. I think, for Mercury, they used to think, well, maybe Mercury processes like it does because there's a planet we can't see. And I'm sure there's other examples out there, but just throwing mass at the problem like that seems like a huge red flag. Now, the nice thing about dark matter is, like I said, it's a lot easier to just throw mass into the problem than it is to change how space-time bends. And that's basically would be rewriting Einstein's theory. And that's kind of what MOND is doing. So MOND is modified Newtonian dynamics. And basically what MOND is saying is when you get really far away from the center of the galaxy, the gravity effect gets really small as well. And so instead of falling off like 1 over r squared like we'd expect, we might get a fall off at 1 over r. Now, the problem here is, how do you define weak? What do you, like, they just basically, you're starting to tune all these parameters to try to get this to work with the measured galaxy curves. And so who is right? Well, they're both not right, but they both are right for some of the time, and they're both wrong for some of the time. So there's really no clear winner here. It kind of seems like it goes back and forth between dark matter and Mond. Um, Now, how does an Aether model actually help on this? Is I'm saying that instead of trying to solve for dark gravity, let's create an Aether model that works with experimental evidence of some of the things that we'll talk later. But if we can make an Aether model that behaves appropriately for how we understand the universe behaves, dark gravity will fall out of um, the theory itself. So now, um, and there's like, that's a huge assumption, but we will slowly, in the next few videos, we're going to kind of move uh, towards that. So why, so why, oh, sorry. So why does an Aether model make sense? Well, we have stuff in the void, right? We have uh, uh, and this is actually this is verified with the Casimir effect and other such things. So we know that there's something in the void. Um, and so it's hard to say that there couldn't be some sort of Aether model as well. Now, the next thing is we know that there's fields that exist. A lot of the current theories that are very accurate rely on fields. What stores that field? Well, could it be? I think you would say virtual particles or something, but something has to store the field. And then the other thing is, how do exchange forces work, right? Like, so currently, I think uh, the biggest or the most common explanation for uh, exchange forces is if you had two people on a boat or on separate boats. This is water. Two people. I'm really good at stick figures. This person has a hip problem. Now, imagine that they're both, um, like electrons or something. Well, in order for them to repel each other, you would basically say that you have a baseball. I don't know why I keep bringing up baseballs. From one person, and they would throw it over here, and this person would lose energy to throw that baseball, but then this person is also throwing a baseball. They would lose energy, but in the process of catching the other person's baseball, energy delta is zero because they're exchanging the same, um, the baseballs or photons of the same energy, and you get momentum, a net momentum, uh, causing them to separate. Momentum for each person would be in the opposite direction. The net momentum of the system is still zero. But anyway, this makes a lot of sense when you're thinking about repulsion, but how do you get this to work for attraction? So if this is now a positive, you have to bring the momentum in towards each other, right? So now you have to somehow, throw your photons away, and like, to me, is it like a weird boomerang? How does this person over here catch this photon over here? I mean, I think the argument would be that the energy level is very low and the uncertainty in the position is large enough, and so it's not really a point particle. And that's my problem, is you're thinking about this as point particles. Really, this is just I don't know. It's hard to explain. I never really like it. But, if this photon over here is moving away with an uncertainty that its position still encompasses that of the person over here, the person over here could actually catch this one. I don't know. Anyway, that seems like a big stretch to me. However, if like the Aether, or your Aether, is storing all of this information in it, you can kind of create a way more intuitive model for transferring momentum. And then finally, things behave like waves. And in order for things to behave like waves, you need to have a medium. And so just like these would be my rough overall points of why an Aether model makes a lot of sense. And the challenge here isn't necessarily accepting these, but is to make progress towards making a model agree with the experiments that have disproven the previous attempts. So I'm going to wrap that up with this for now. Okay, so in the next step, we're going to go a little bit more detail into why an Aether model makes sense. Then we're going to look into why an Aether model doesn't make sense. And if we fully commit to this idea, what are the actual biggest challenges to an Aether model? And I think that is probably one of the less well-known or understood problems for moving forward. So please stay tuned and follow for future. I'd like to make this a discussion, so if you have comments, leave them down below, but I look forward to hearing what people think, and we will continue this discussion here soon. Thanks for watching.